So this is my project. The title is Hybrid of Grid Renewable Energy System for Remote Communities, a case study of Balacola, BC province with microhydro integration. So I separate into three parts. The first part is introduction and background, like the remote community energy challenge in Balacola. The diesel reliance cost energy insecurity, high cost and environmental concerns. So our goal is to minimize fuel consumption, ensure around energy availability, and reduce the LCOE. And now let's talk about the hybrid renewable energy systems, like sustainable energy transition, hybrid renewable energy systems. So combine multiple renewables with storage for reliable off-grid power, improving reliability and reducing cost. And here's some benefits and challenges. So let's turn to part two. Part two is about system modeling and main contributions. For the system modeling, design an optimal hybrid renewable energy system for Balacola requires care for integration of climatic data, energy resource characteristics, and community demand profiles. All the renewable source data were collected from NASA Surface Meteorology and Environment Canada database. So like monthly average value for wind speed at 50 meters height, solar insolation, and river discharge were analyzed to determine seasonal availability of energy sources. Like the stream flow rate data reveals a significant seasonal variation in hydro resource availability, with peak flows occurring during the snow melt period and lowest level observed in winter. These trends imply that hydro generation can serve as a baseload source during spring and summer, while battery or diesel support may be required in winter to maintain the system reliability. So also you can see the load demand. Like the load profile for Balacola was derived based on typical residential or and community scale usage in off-grid indigenous and remote Canadian communities. A daily average electricity demand of nearly 21,000 kilowatt per day was assumed, with the peak load reaching 1.32 milliwatt during winter months due to heating and lighting requirement. So what we have done is we created 6 hybrid system configuration. They modeled by using Homer Pro, each including various combinations of the following components, like PV, like wind turbine, micro hydro, small hydro, like battery energy storage system, diesel generator. So we use the same type of PV wind turbine and battery, also the diesel generator. Then we changed different types of hydropower, like micro hydro, like small hydro, like moderate hydro. So that's the 6 model configurations. We also do the sensitivity analysis, like diesel fuel rise, price increase, or river flow reduction to simulate the dry years. The table 1 shows the summary of several hydropower turbine parameters. All the hydro systems are assigned a 30-year lifetime consistent with mechanical expectations for hydroelectric infrastructure. Turbines were selected to reflect Balacola's topography and hydrology, favoring low-head, high-flow designs, which are typically of coastal mountainous rivers. So this is our main contributions. The first one is this table 2. The Homer Pro simulations yield key performance indicators, including LCOE, renewable energy fraction, diesel generator runtime, and excess electricity production. A summary of results is printed in this table. Like Model 1 achieved 100% renewable fraction but suffered from very high excess electricity, and LCE is also very high due to the lack of dispatchable or baseload sources. Also like Model 6, which use a larger hydro unit, is a small-scale hydro, improved renewable fraction to more than 90%, but incurred higher excess generation and system complexity. So all these results demonstrate that microhydro integration significantly reduced diesel usage at cost, while also improving the load matching. Also, we do the sensitive analysis for the river flow reduction 20% off. The renewable fraction is lower, diesel generation is higher, like LCE is higher. And we use the Model 6 as a base model. Also for the diesel fuel price, when the price increased from 1.2 to $2 per liter, the net present cost rose from 30.5 billion to 35.2 million, and LCOE increased from 0.308 to 0.356. Also, the annual cost also increased from 1.16 million to 1.49 million. So let's turn to part 3. Part 3 is about conclusion and future work. So, like the study presented a comprehensive design and tech economic evaluation of a hybrid off-grid renewable energy system tailored for Beta Cola, a remote coastal community in British Columbia, by modeling 6 different system configurations in Homa Pro, like varying combination of PV, wind turbine, microhydro or small hydropower, diesel generators, and battery storage. The research aimed to identify a configuration that minimized fossil fuel reliance, lowered the LCOE, and enhanced the year-round reliability. So among all these 6 configurations studied, like Model 4, which integrates PV, wind, medium-scale microhydro, diesel backup, and battery energy storage, demonstrated the most favorable balance. The LCOE of this system is about 0.308 per kilowatt hour, and the diesel generation has reduced to 17.2%. The renewable fraction achieved 77.7%, while the excess electricity has kept moderate. Also, the sensitive analysis further emphasized the importance of robust design against environmental and economic uncertainties, like a 20% reductions in hydro flow rate represented high dry years caused a significant increase in diesel usage and operational cost. Also, the diesel price increased from 1.2 to $2 per liter, raised the NPC by over 15%, underlying the viability of hybrid system to fuel price volatility. So all these findings reinforce that microhydro integration is not only technically suitable for Beta Cola's landscape, but also economically impactful. It enables higher renewable penetration and offset the diesel dependence, particularly when paired with intelligent seasonal dispatch strategies and adequate energy storage. So for our future work, like first of all, we need to solve the resource load mismatch, like the Beta Cola's river flow peaks in late spring and summer, probably due to the snow melt. However, load profiles indicate that peak energy demand occurs in winter, primarily due to the heating or lighting needs. So meanwhile, no, sorry. So that will cause two situations, like when the hydro output is high, while load is low. So that will increase the excess electricity. When the hydro output is low, while the load is high, the system will have a greater reliance on diesel or battery storage. Meanwhile, batteries are particularly buffer this mismatch but may not fully eliminate the diesel need. So in winter, a rule-based mismatch, like the figures below, where batteries serve peak mid-peaks and diesel fills deep gaps is necessary. Also, as a future work on a control model in Simulink will be developed to simulate real-time energy management strategies, particularly focusing on hydro-diesel battery coordination and seasonal constraints. This addition is expected to enhance the system's dynamic performance evaluation and to provide a more realistic control framework for future implementation. So that is all. Thanks. Thanks for listening.